right. Hey everyone, welcome to the stream. Right, let's see what we have to do today. Yesterday we were done with branching commands. Okay, so today we'll start with the function commands. And for that we'll start with the parser first. So what will it look like? Let's see how this function commands, how exactly they look like. So these are the branching commands. Let's skip to functions. Function. All right, so this is how the syntax of call will look like. Wait, is that it? No, this is just a sudo vm code. So what's the final vm code? So the function syntax will be like this. It will start with function and it will have two arguments. First the function name, and second an integer which represents the number of local variables. All right, so we have already taken care of instruction types for function, return and call, so we don't need to worry about that. But what else? Now we need to modify this argument methods. What's the syntax of call? All right, so this is the syntax of call. It also contains two arguments. It starts with call and second argument is the function that is being called, and the second argument is, so I'm going to call this as first argument and this as second argument. I'm not going to take this one as an argument, just a instruction name. So this is the first argument and this is second argument. In case of call instruction, the second argument it represents how many arguments are we passing to this function. This 2 represents how many arguments from the top of the stack we are passing. Okay, and what about return? So return doesn't contain any argument, it's just the instruction name. So let's write the logic for call first. So if self dot type equal to c call wait, in this case as well we don't need to get a different condition. So let me get that, and I should directly pass it over here. or okay, because in this case as well, in case of call, we will split the instruction and pass the first element for argument 1, and same will be the case for function. So let me copy it up to here. Let's change this to function. If self top type equal to function, then also we'll split and pass the first element. But now in case of return, well, we don't have anything as an argument, so we don't need to return anything. It will be just none, so we don't need to write the condition for return. And that is it for argument 1 method. Let's write this argument 2 method now. Again, in this case as well, you can write the logic inside this first condition, because we are going to split the instruction and pass the second element anyway. Self dot type equal to C call, or self dot type equal to C function. Okay, we are done with the argument methods. What else do we need to do? Okay, now comes the hard part. We'll have to write the modules for writing the instructions, but before that we will have to figure out what kind of instructions, what kind of assembly instructions we are going to write. And let me tell you, they are not piece of cake. There's a lot going on. That means we'll have a lot of bugs. So I think before we get started with implementing the logic, I should review the slides. It will be easier that way. Let's see, functions in the VM language executing. If this is the high level program, it will be translated down to this kind of VM code. Not translated, compiled, and this will become this function mult2. This 2 represents 2 local variables. Then the instructions for all of this code, and finally we will have return, and we are going to return sum. So whatever we are going to return, it should be pushed on the top of the stack just before this return inside the VM code. Okay, I get it, but this is just the logic for the function. But before, this is how we can call the function using call mult2. This is another function, main function. This will call this function mult. That means this is the caller and this is the callee function. First we push 3 on the top of the stack, then 8, then 5. After line 4, call mult2. This 2 represents the two arguments, and those two arguments will be from the top of the stack. So 8 and 5 will be passed to this function, and this function will do the computation on those two values, and whatever is returned should replace these two values. So when we call mult 8 and 5, it should multiply 8 and 5 and return us the result and replace it on the stack. We get 40. After that we add. That's easy. Adding, we have already taken care of it. So if we pass mult 2, that means the two segments of this stack becomes the argument segment for this callee function. Okay, and this function has its own stack and its own local segment as well, and this will be initialized to 0 according to this argument. So if we have two segments will be initialized to 0. Determine the return address with the callers within the caller's code. Save the caller's return address, stack and memory segments. Pass parameters from the caller to callee and jump to execute the callee. This is the overall thing which we will be handling when executing this instruction call. These things we will have to implement inside the assembly code. What do we have after that? In the callee function, initialize the local variables, okay, and handle some simple initializations. And in case of return also, we'll have to take care of these points. Function always ends up by pushing a return value on the stack. Okay, return the return value to the caller. Okay, recycle the memory resources used by the callee. Okay, that means destroy the local and argument segments, not exactly argument, maybe. So destroy those segments so that other functions can use that memory. Reinstate the caller stack and memory statement. Okay, and jump to the return address in the caller's code. That was the implementation overview. During the runtime, each function uses a working stack plus memory segment. Working stack and some of the segments should be created when the function starts running. Maintain as long as the function is executing this cycle. Okay, these 3 points we'll have to keep in mind. Maintain the stats of all the functions, the calling chain. maintain the states of all the functions of the calling chain. Okay. Can be done by using a single global stack. All of the segments of all the functions will be inside a single global stack. Okay. Call a stack after. Okay, this function says call foo and args. When we call this should happen. First argument pointer should be set at this location, and this location will be calculated using this and args argument. This is just a working stack of the caller function. The stack becomes the argument segment for the callee. Okay, after that we save the caller's frame. We save it after at the top of the stack. So we save the return address. Okay, save the return address. So we save local pointer argument this and that of the caller. And only after that we are going to execute the foo or the callee. After that, the first thing we will do when we start executing the callee function, we will first set up the local segment. Okay, local segment. This is how it will look like. First we assign the local wherever the stack pointer was, we assign the local pointer at that position. Now this local pointer is for the callee, and we increment the stack pointer based on how many n was specify the number of local variables. We will increment the stack pointer that accordingly, and also will initialize all the local variables to 0. Okay, after doing the assignment of local variables, we will start executing the instruction inside the callee function. So this will be the working stack of the callee. The callee prefers to return it pushes a return value. After we are done with, when we come up to the return instruction, that means the function is over and we are preparing for returning, and whatever value is on the top of the stack will become the return value. This is how we will handle the return. First we will get this value from the top of the stack and copy it side argument 0, and after that set sp for the caller. This sp should be pointing to this value after we are done with this returning. For that, we restore the segment pointers of the caller. Jumps to the return address within the caller scope. We will jump to this return address, and all of these values will be destroyed, not exactly destroyed, but they will be recycled, or I can say it will be in a state where we can reuse that memory segments again. It will look like this. Everything after the stack pointer will be will mean nothing. And that was just for one function call, but we will have many function calls. So this is how the global stack will keep on increasing like this in a stack manner. This Right, so where was I? Okay, I was saying there's just one global stack, and all of the functions, stacks, and memory segments will be stacked in this manner. For that direction, this is what happens. So when we call this, something happens, and after that the caller resumes. So whatever happens inside this is what we have to implement. Okay, we have seen the runtime simulation. No, we are going to see the runtime simulation now. Okay, this is what happens when we run this main function. At the global stack, we will have 3. After that, we call factorial 1. When we call factorial 1, this 1 represents that we have to pass 1 arguments from the stack. That means this will become the argument 0 for this factorial function. After that, we move. Okay, we save the frame of the caller, and after that we get started with implementing this function. Let's not go through the runtime simulation. Maybe we'll come back to it again if we are stuck at some point. Let's just skip it and okay, now we are going to see the detailed implementation. So the call function returns the argument values that I pushed before the call have disappeared from the stack, and a return value that always exists appears at the top of the stack. After the call function returns, all my memory segments are exactly the same as they were before the call, except that temp is undefined and some of the values of static segment may have changed. before I start executing, my argument segment has been initialized with the argument values. So this is for the callee, my local variables. Okay, initialize 0 static segment has been set to static segment of the VM file to which I belong. This is a rough outline of how the assembly code will look like. Okay, we'll have a function. Inside the assembly file, a function is just a label like this one, where we have to jump. Is assembly code that saves the caller state on the top stack. Get this thing, but what about this? Sets up the function call and then go to. What do you mean set up the function call? Also function informing that an args argument have been pushed onto the stack. Generator. generated by the translator. First we have to push return address. After that we push local. That means basically saving the local of the caller. That we save argument and this, and after that. Once we are done with that, we will reposition the argument. So this argument should point to the starting of this n arc. So what will be the position? It will be stack pointer, wherever the stack pointer is right now, minus 5 for all of this, for this 5 memory segments, return address, save local, and minus n arc. So if there are 3 arguments for this callee function, we will subtract 3. So this will give us the 0th index of this argument, basically the base location of the argument segment. That will be the argument segment for the call E. See, now the argument is pointing to this location, and after that we'll also reposition local pointer to stack pointer. Okay, initially the local pointer will point wherever the stack pointer is pointing. After that only we will go to the function name. This is just a pseudo assembly code. We have to implement this instructions. Return address label. We have to provide a label as well after this code too, so that we can return to this label after we are done with the callee function. This is what it will look like, the return address label. $return.1. What the heck is this? So foo is for the function from which we are calling another function. $return, it's just a generic thing, but dot and 1. So I guess this one is for the first call, and suppose we have 2 calls inside the same function. The second function return label will get $ret2. Yeah, I think so. Now we'll see how to implement this function instructions. This is what we'll do inside the function. Repeat n var times. What do we have to repeat n var times? Pushing 0, which is basically initializing the local variables, and n var is how many local variables we have. So if it is 2, we will push 0 2 times on the top of the stack. Okay. Okay, so that was it for the initialization of function call function. After that, it will do its function execution, and now we have to see how to handle the return. This is the work done by the callee. Now when it comes to the return statement, this is what we have to do. We will store the local pointer inside a temporary variable and frame. After that, we will get the return address. Return address will be end frame -5. So this is 1 -2 -3 -4 -5. We'll get this return address and store it inside this return address variable. Now we will pop the value, this value, and store it at arg, and this arg is pointing at argument 0. So we'll store this value, which is basically the return value. Return value. After that, we reposition the stack pointer. Where do we reposition it? Argument +1 at this position. Now we need to restore the segment pointers of the caller function. So that will be end frame. End frame is pointing at this location -1. So this saved variable will be now become the tet pointer, and this again arg and local. After that, we'll jump to the return address. Return address, which was stored earlier inside this variable. Okay. Okay, we have reviewed all the steps, and I think it won't be as much difficult as I was thinking. But before that, we have to take care of the steps as well. So now Suppose we have a, this will be the higher level language jack. It will be compiled down to this kind of VM code. Now this VM code might be inside two different files like this, foo.vm, var.vm inside a single directory. And our VM translator have to keep in mind that if we are giving a directory name to a VM translator, we should translate all the VM files inside the directory inside a single assembly file. Okay, so that means we will have to modify this code writer as well as code reader to keep in mind the directory name. Okay, so we'll have to probably keep a check condition which will check if the system argument given is a file or if it is a directory. This is the convention of the VM program. Main. The stack starts in address 256 in the host RAM. When the VM implementation starts running or is reset, it starts executing at an argumentless OS function named sysinit. Sysinit is designed to call main. This is the main file and main for the main function and enter an infinite loop. Bootstrap code. So, stack pointer at 256. Call sysinit. Is this like a bootloader or something? Bootstrap code? Maybe. So this will call sysinit. Wait, this xxi is for static variables. What did we implement in case of static? Oh, argument 2. Wait, but this seems incorrect because wait, yeah, it isn't. It is correct. Okay, it is correct. It is correct. Doesn't matter. be right back, guys. What the fuck? 148. Let's okay, let's try to write the logic for this, whether the input is file or a directory. So we'll have to do it inside main function. First of all, we will check. Well, before we do that, let me try to run the code. Seems to be working. When I try to, before I try to open it, first I will have to check if this is a file or a directory. So how can I check if the given string is a file or directory? Python. If not, os.path exists, os.path their name. Okay, we do have os path is that, but os path is directory. So let's try to check this. What we will do, if os.path is directory, and we'll pass the system dot argv1. Print let's see, print this directory, and after that we will print the whole path. Is path dot abspath sys dot argv1. Right, and if it is not a directory, in this case also will print something. Print is file, comment this code for now. So if I pass this, it's 5. Now if I pass this, still it is a 5. But if I pass, it's directory also. And what if I pass a relative directory? Something like this. Simple function dot vm. It says it's a file, and if I pass this, it's the directory. Okay, it is working as intended. So what do we have to do when it is a directory? Well, in case of file, we go back to the slides. So if we have passed just the single file, that means there's nothing much to do. We just have to open it up for reading, and after that we will close it and write to an output file. But if it is at a directory name, it will contain one or more vm source files. But is there a convention for choosing a particular VM file from one or more VM files? There was something about the main file. Where was it? This, I think. Main, not main. One file in any VM program is expected to be named main.vm. One VM function is in this file is expected to be named main. Well, in this case, we don't have main.vm. We have foo.vm and bar.vm. And this will be translated to foo.main, foo.blah. Can we change the order of this file? Not file. Can we change the order of this methods? We have to write this method right init. Yeah, main.vm sys.vm. Just sys.vm. Okay, let's check what is inside the sys files. Function calls, Fibonacci element, name. Okay, call main.fibonacci 1. This is the bootstrap code. What else do we have? We have main. This is what we will call after the sys call. In the sys call. Now let's check the nested call. We just have sys.vm here. Okay. Statistics test. We have class 1, class 2, and sysvm. Okay. So we should probably start with the sys.main file. Yeah, we should start with the sys.main file. Because it is this dot main code which is going to call the main function, other main function. So yeah, before we do anything, we should open the sys.main file, and its code should be at the initial location of the assembly file. Okay, so okay, let's see what we have to do. Let's write the logic for files first. If it is a file, wait, you see now this things we have to call again and again for all the different files. If we have multiple files inside the directory, we'll have to open it up, write the code, close the file, open another file, and so on. That means we should write a function for this lines of code. Where should we place this? What are this guy suggesting? was I trying to find? I forgot. Oh yeah, the implementation details. Mm. Let's just write a function over here. We call it setup. We should pass these lines of code. Yeah. And we'll probably pass the path. Okay, let's see what we have to do now. If the argument is a file, then we'll call setup and we'll pass the file. Before that, let me just get the absolute path. And we'll store it inside a variable path. Okay. Pass path here, and now we don't need to write everything. Here I can pass the path for now. Okay, and we can pass this part to setup directly. Now if it is a directory, what do we need to do? We need to call setup for all the files. So but first we have to call setup for the sys file. If it exists, we should start with the sys file, then everything else. So we will probably have to use for root and files in os.walk paths print root root there's files so let's see if I pass this, what happened. Yeah, we get the root. This is the root. Inside does, because we don't have any directory, it will be empty, and we will have files. This is what we need. We don't need to take care of the root. We need the files. So now what we have to do inside this files, we will have to check if there is a sys.vm or not. If it is, then we should call setup on that file first, and after that we can take any of the other files. But if there is no sys file, we can take any file, any VM file. We'll also have to check if those files are VM files or not. List. Check if a string is in just Python. I think we can use is in. check if sys.vm in files. In this case, we should call setup os.path.join root, and well, I need to get that file. I can directly pass it. This dot vm. Awesome. If it does have a sys.vm file, we'll call this. After that, we will do for file in files if file equal to sys.vm not equal to sys.vm, then we'll call setup os.path.join root file. I don't have to provide the DIRs. No. Okay, this seems correct. What we will do here is, first we will walk through the, wait, we don't need this, so if sys.vm is in files, then in that case we'll call sys setup os.path.join root sys.vm. This will open up the sys.vm file for reading and then writing. But after that, we will do this file for files and files. Well, we don't even need to check for this condition, because as per the convention, if we are passing a directory, that means we should have a sys.pm file anyway. Well, it doesn't. Wait, but what if we are just passing the file? Don't we need the bootstrap code in that case as well? Let's check something. Fibonacci series, this simple function. Inside this, we just have a VM file. Okay. All right. But there is still something. Let's see, there's still something missing. So even if we pass this file do this setup. I still need to get output file. Oh yeah, this is what we need to change. Right. We still need to create an output file. So now in this case we can't directly open up a file with this name because this can be a directory as well. And if it is a directory, let me check if it is a directory. What assembly instruction that affect the bootstrap code that initializes the VM? Okay, if we already have the sys.vm file, why do we need to write the bootstrap code by ourselves? I see. Do we have to call this to write the assembly instruction for init? This is confusing. Let's worry about it later, but first let's see what output file should we have. Should be either the file name or the directory name. Okay. Well. Let's check the condition here as well. If copy this, path, if path, what was the command again? Os dot dir isdir os dot path is dir. Os dot path is dir path. If it is a directory, let's see. We'll have to get the directory name. The last directory from the path file. Okay, let's use this OS norm path, base name and norm path. Base name equal to OS dot path base name OS dot path norm path this will give us the directory name. What we will do after that, we'll change this path to its path is equal to path plus this name. Wait, we might or might not have a slash at the end. Yeah, let's use the join command. Start path join path name plus dot esm. Else do we need to do anything? No, we don't need to change anything if it is a file. No, we do. If the path is a file, in this case we will do path is equal to well, I can't split with the dot. So what we will do, get file name and extension from path Python. Split text. You can use os dot path dot split split text, and we can pass the path. path is equal to path plus dot asm. And so now what we can do, we can pass the path here. But there's a problem now. See, we are initializing the code writer every time for each and every file, right? We're getting a code writer for each and every file. Does that change anything? Parser will work all right, but what about this? Yeah, so it will mess up this line count and LT count and all of these variables. So we need to write all the code writer only once. You can call it every time. Okay, so we'll remove it from setup and place it over here, I guess. Let me write it over here. It doesn't matter. But it will have an implication because we are calling this code writer. So either we have to pass this code writer to setup, well, you know what? instead of calling the setup here, I can cut this everything out of. Well, then what's the meaning of this setup? Oh, what the hell, let me just remove this setup. I can do this. Walk, read. Read VM. In this code, we are reading the VM instructions. Yeah, I will call this method read VM. No, the heck, this won't work. Let me just pass the code writer here. Not here, we'll pass it here. Now what we will do, We'll pass the code writer in the setup. Code. Okay. This will work. So now we are opening the file for writing only once. Let's see, first we are getting the path, then we are opening the file for writing, which is correct file. Now after if equal to path is a directory, then we walk through the directory, and if there is a sys.vm in files, we'll call setup with that vm file and the code writer. So, and if there are multiple files, if the file is not sys.vm, we'll call all those multiple files. Okay, we need to pass code over here as well. So let's see if it still works or not. So if I pass this simple, what happened? IO operation. Okay, I see. We are closing the file directly here after opening up just one file, so we can do that. We can call this here. Okay, it works without. Oh, hey Jen Pong Tong, how are you, man? Yeah, I am that guy. The one who was talking about the OS, right? Yeah, I am that guy. We talked earlier. You came to my stream few days ago, I think. And we talked about your code, and I checked your GitHub profile and all that. Translator.py. So it is working for a directory. Let's see if it still works for a program file or not. So just program file. Oh, it gave a program flow.asm for all the assembly files. Just check for Fibonacci series. Fibonacci series VM. Before we do that, let me save the file first. P08 program flow Fibonacci series Fibonacci series. What's up with your emulator, bro? How is your emulator? You are working on a cheapet emulator. Oh, you also stream. Good. Let me check your stream. When did you started streaming, man? It seems that you have streamed just once. How did you get all these views? 66. And you have got 19 followers. Good. Oh, all right. So how long have you been streaming then? Just started. What do you mean just started? Like a month before or something? 2 weeks? No way. Great, man. So I started streaming like a month ago and I have just got like 7 followers and you got 19. Awesome, man. Nice going. Fibonacci series dot ESL dot. Okay. Yeah, no, I don't. It doesn't matter to me that much. But I was just, surprised that you got this much. Like, maybe it is because you have been interacting with a lot of streamers, I guess. streamed 9 days ago. So when are you going to stream again? Maybe I will come on the stream and we will have chat again. One of the series. 18, 19. Alright, sure. I will come on stream. Python, HTML, CSS, Django, commerce. Okay, so you are building that commerce site that you showed me earlier. Good, good. By the way, I'm not aware of that GPAT emulator. What does it do anyway? What does it do exactly? Yeah, I'm asking about that emulator only. What does it do? Oh, chip 8. Chip 8 emulator. Let me Google it. No, I don't think I have an idea. Except yeah, I think I already have the link to your project. I checked it earlier. But I just want to know what it does. So I have a rough idea. Like I saw this video about from a YouTuber guy. He made a chip 8 emulator. I think he played this retro games like Space Invaders and all of that games as well. Chip 8 project comes with a bunch of code. By N64, do you mean Nintendo 64? And GB as in Game Boy, right? Oh, cool. That sounds cool. Maybe I will also try to make something like that. What exactly is the chip emulator? What does it contain? Because I think it is an interpreted programming language. Initially used on okay, these are the kind of instructions that we fed to this chip emulator, right? Let me check it out. I'm interested in this because what I'm trying to build is somewhat similar to what chip at emulator looks like. The link doesn't work, man. Yeah, you mean it's because of Brave? Okay, let me try to use a Firefox then. Hosted in pot. Wait, even Firefox is not opening it, it seems. Okay, that means the last resort is Chromium, or maybe Chrome will open it up. Even Chromium is not opening it up. Do you have any other link? So I'm trying to. Sure, actually, I'm interested in it because what I'm doing right now is, I think, somewhat similar to chip at emulator. It's just that, okay, let me try it inside the Firefox. 1997. Okay, what if I try to open it up with curl? What the hell? Nothing, it's just empty, not found. Okay. It's still not found. I don't know, man. Maybe, maybe not. I'm not using any VPN or something. Maybe my internet connection is blocking that website. Let me try to look at your code. Chip it. This is your repository, right? Pong chip it emulator is a simple interpreted programming language which was first used on some do-it-yourself computer system. Okay, what are you doing over here? First, keyboard and renderer. Init. First you call init. Step renderer. Step then step renderer dot main renderer dot py. Yeah, it's all right. Let me see, set pixels, clear render, set pixels, and self dot render. CPU dot py. Okay, so first you are initializing a memory of 4000 kilobytes, it seems, right? 4000. Vi is equal to 16 into 16. Vi data timer stack was PC. So this is the program counter, right? Self.pc. No, I have no idea how to do that. Load rom.data file name. So one rom, after that you enumerate on this data and store it. Okay, so this rom must contain the bootloader or something, right? Let me open it up. Rom's picture. Wait, what kind of file is this? Just a ROM, but what does it contain? Oh, it looks like garbage. So is it in binary or something? Yeah, right. Okay, I see. So it is in binary. That means, and it must be compiled using the specifications of this GPAT emulator, right? So I think it might contain the code for initializing the stack and for input as well as graphics and all that. Okay, so no. Okay, then what does it contain? Convert binary to hex. Yeah, I can use. All right, let me try to use Python then. Can I use this? Or this won't work? What if I use it like this? Okay. Can I do this? Then x file dot read. Will this work? No, it doesn't seem to work. Yeah. Yeah, but for data in file, we'll try to find new line characters as well. That won't work. That's what I tried to do before. See, for f in file. Let me try to do what you are trying to say. What? Can't convert an error occurred. It seems to be not working. So yeah, let's see. So suppose if the instructions are in hex, but those instructions adhere to this, right? Like the hex code is basically this commands, right? Opcode, type, and so on. If we convert those hex code, what you are doing is speaker render keyboard. This is your main file, right? First calling the init, and while true, pygame screen. Will this data? Okay, let me try to use it. Okay, RB, read binaries. For ij enumerate data print ing. Awesome. Zero zero. So I guess this is the first column is for the line numbers, right? The first column is for line numbers, I guess, and the second might represent the instructions in integer format, right? Is that it? Okay. So should I do something like this? X. Okay. Is this the correct way? Okay, so the I is also in X. Oops. Oh, okay. So is this first column like opcode or something? Instruction set for the picture to load. Okay. Yeah, it is opcode, right? And what about the second column? These are the arguments, right? Has 35 opcodes, which are all 2 bytes long and stored big endian. It's listed below in hexadecimal with the following symbols. You mean 2 byte? So it's here. It's here 0 and cause machine code routine at address and not necessary for most ROM. So this NNN must be like an address for this call. So whatever we pass to NNN, it should call that specific function, right? 00E0. It is just a display 00EE. This is for the condition 3xNN. So X and Y are 4-bit register identifier. And this will check for if Vx is equal to NN. Okay, so what I'm trying to build right now is also somewhat similar to this. So in my case, the code looks like this. Let me show you. Yeah, actually I built everything from scratch. So from Nand gate, I built all the other gates from Nand gate, and then let me show you what exactly I built. So if I walk you through everything I built. So first I built all these chips, not and all these mocks from Nand gate. From the basic, I was just given this Nand gate and I built all of this. After that, I created half adder, incrementer and ALU from this chips. And for project 3, I built this data flip-flop, then bit, register and RAM and a program counter. After that, this was just assembly programming. And after that, I built a memory unit, a CPU, and finally a full computer. Not physical computer. I built it using a simulator. Yeah. So this course has provided a simulator. And after that, I built an assembler which converts this assembly language files into binary. And right now I'm trying to create this VM translator which will convert, let me show you. It will convert the higher language in VM code into assembly language. Yeah, sure. For what do you want to see the code? Because it is like segmented. Let me try to show you. Sure. So for logic gate 0 1. So, and this logic, all of these logic gates are built using a language called HDL, hardware description language. It is similar to Verilog. It is similar to Verilog if you know about it. This language is used to create, a simulation of all these logic gates and much more. This is what actually the industry professional use to build the CPU chips. So this HDL is somewhat similar to Verilog. Let me show you the implementation of AND and .hdl. This is what it looks like. We are given two inputs A and B and we have to produce the output, and this is what the code looks like. First we pass A and B as an input to NAND gate and we get the output inside W1 variable. Now we pass this W1 variable again to another NAND gate, and this NAND gate we pass it. No, not exactly. It doesn't teach everything, like it doesn't provide course and all. It just guides you and you have to figure out all the code. The course is on Coursera. Let me show you. It doesn't provide all the code and it doesn't walk you through each and every step. It just so that they just basically guide you, like how is the logic of AND gate and all that, but you have to implement everything. So this is the first part of the course. In this we build this logic gates and ALU and memory and machine learning, so and computer architecture and assembly. But this is just the first part and I have completed it. Right now I'm going through the second part. Let me show you. In this part we are going to create an translator, a VM translator. Then after that we'll build a compiler for a higher language. The language is Jack, which is almost similar to Java programming language. we'll build a compiler for that language, and after that we'll build an operating system. So this is not a fully fledged operating system. It's just, a toy operating system, but it will include most the important parts. I am at this point right now, week 2. So I'm trying to create a VM translator right now. After that, the compiler will come. Yeah, sure. We'll talk again then. Maybe I will come on your stream when you try to build the emulator. By the way, if you want to watch the video, this is the one I was talking about. Okay, so where was I? We were trying to compile the code. Did we compile it? Stack arithmetic. No back file. It is inside the program flow Fibonacci series dot back. Okay, let's go to that folder then. Program flow Fibonacci series. Let's not move that. We have assembly and assembly.pec file. Okay, let's try to compile a new assembly file now. Program flow Fibonacci series dot bm. All right, we have a problem. Can only concatenate tuple, not string to tuple. Oh, is this a tuple? Ah, of course it is a tuple. And the binding stopped working. I have to close the beam and open it up. Okay, let's try to translate the code again. Okay, it worked this time. All right, so our program is still working. Both of the files are similar. Am I using difference correctly? Def command. Okay, that means the two files are identical. Let's try to compile it again. Awesome. All right, now that we know we didn't mess up the program, we need to do. Where was I again? Yeah, we just wrote the logic for opening the file for writing it. That. Let's see. We still need to write the logic for functions. What am I doing? Set a code if bigger type is equal to arithmetic load. Okay. Let me go back to the code. We have taken care of this logic for multiple files, directory name, construct a parser to handle the input file, and so on. Let's see, what was that sysinit file all about? Where was it? Oh, right, this is the code. Even though, all right, I get it. Let me open up the sysinit file. Fibonacci calls, Fibonacci elements. So sysinit file just contains a function, but still we need to call the function sysinit. So for that we do need this bootstrap code. Okay, I get it. We assign stack pointer to 256, and after that we call the sysinit. But wait, there's something missing. Where do we initialize this other segments? So SPD is equal to 256 means what we basically do is change this first RAM register and store 256 inside that register. Oh wait, I'm getting confused. So this code should be written. Let's check the test file. tst, yeah. Wait, this doesn't do anything. It just loads the assembly file. Uh, what about other files? Function calls, simple function, tst. Well, we do need to take care of inside this test script. We are taking care of the initialization of segments. We are setting RAM0 stack pointer at this location. This local argument, this and that. After that, we set the local. This is no, this is argument. We set argument 0, 1, 2, 3, 4. Argument 137, and we set 6 arguments. Okay. But this is just for simple function. But inside the Fibonacci function file, Fibonacci element, we are not taking care of this. Let's check this vme.txt. We are just setting the test stack pointer to 261, but inside the emulator tst, we are not even changing the stack pointer. So does that mean we have to do it manually? Which files do we have? We have a main.vm and sys.vm. Let's check this main.vm. Let's just contains this Fibonacci function. Nothing interesting. Sys.vm. It assumes that we have already initialized. Okay. They're suggesting that inside the bootstrap code we assign the stack pointer value, but what about this other values? Don't we need to take care of these values as well? And this is messed up. Writes the assembly instruction that affect the bootstrap code that initializes the VM. This code must be placed as the beginning. Yeah, I get it, but why are we only initializing the stack pointer inside this bootstrap code? Let's open up the virtual emulator. Try to load that test script, which was here function calls Fibonacci element VM. We do over here. Wait, we already have this sys init. Sys init 0. We are calling the sys init function. Okay. Ah, I see now. All right. Oh, yeah, yes. So when we call this, so I was stuck inside the previous logic, like the logic of the previous test functions. But I see now. When we call this function, at that time we have to initialize this local and argument, of course. Okay, I see now. Let's try to walk through this program now. I see now. That's the code. That's the code. That's the code. Right, this is the only thing we need to take care of inside the bootstrap code, because the initialization of argument and local will happen inside the function. I see now. Good. Okay, so that means we will have to write something inside this code right there. SP256. What do we need? Write init. Yeah. Let's get a function or method, whatever you want to call it. Write init. This will write the bootstrap code, and we will call it the first thing inside this init. And when we open up the file for writing, After that, we'll call. Well, let's call it here. What happened? We'll call at the last self dot write neat. Okay. Here we'll write the logic for the bootstrap code. What's the bootstrap code? Okay, this is what we have to implement inside this write init function. Sp is equal to 256, then calling it. Okay, but first I will have to figure out the logic for this call. Okay, we'll see. But right now I think I'm going to take a break for lunch. So I will see you guys after lunch. Sp is equal to 256, calls init. Alright, then I'm going to take a break now. See you guys soon. I'm back. So let's start writing this code. Write in it. What we will do here, let's first get a string. Before we get a string, let's try to write the logic for this code. Okay, so what should be the logic? First, we have to assign 256 as the stack pointer value, and the stack pointer value is stored at RAM 0. Therefore, we'll have to get RAM 0. We can select R0. This is basically the first register or RAM 0. Before we do that, we need to get 256 value. So first let's get 256. D is equal to A. We'll store the value 256 inside data register. Now we'll select R0 and we'll do M is equal to P. This will store 256 inside the first register. So this will assign 256 to the stack pointer. After that, we need to call sysinit. So now this is the hard part because there's a lot of involved. We'll have to check sysinit, call sysinit 141. So before we try to write this init code, we'll have to figure out the logic for this call operations. So I'm just going to pass on this method for now, and we'll write another method which is we'll start with write call. Definition write call. Here we'll figure out the logic for call, but before we do that, write call number of arguments, function name, string. What should we do in this method? Will we be having this kind of conditions? This call will have function name and number of args as argument. So I don't think we need any conditions, right? So I will just copy this. If parser dot type not equal to C call, then return. Now we'll get parser argument 1. Don't need this, right? The command over here. Call commands. Let's figure out the logic first. Call instruction. It will be something like this. Call function name and number of args. So now let's check the logic. I need a detailed instruction, detailed implementation. Where is the detailed implementation? Yeah, it is here. Well, before we write code for write call, we need to write the code for function, because that's what the first test code checks for. So let's do that. Write function, and we need to pass self and a parser here as well. We need to pass self and a parser, and let's comment this out for now. Before we handle the call, we should handle the function. So let's skip to handling function. This is what we have to test. Performs a simple calculation and returns the result. This is a test for function and return. So we'll have to implement the instruction for those two statements. This is what we have to do. Function syntax will be like this: function name and was. First we'll have to generate a label, so you can directly write something like this. Function name will be inside argument 1. This will be the first instruction for the assembly code. After that we have to push 0 NOR times. For that we'll have to get the stack pointer first. Wait, we probably need a loop. Let's just write a code for assigning 0 just one time for now. sp is sp what we can do, a is equal to m. So now a contains 256, and if I do m is equal to 0, this will initialize that position as 0. After that I need to get the stack pointer again, and I need to increment the stack pointer, and I will have to carry out the steps n vars number of times. So I will have to get a loop, but first I will have to for how do I get a loop? Let me write the pseudo code first. What's the spelling of pseudo? I hope this is correct. First we'll do arg1, then we'll have a loop for while let's say we'll have a variable I equal to n vars while I is greater than 0, do sp equal to 0, and after that sp equal to sp plus 1. Also I minus minus, or I should write I is equal to I minus 1. Okay, so let's get the I variable first. Before that we will need the value of n vars, so we'll do n vars. N vars is inside argument 2, so we'll do argument 2 d is equal to a. Now data has this value. Now we'll get the variable I, and what we'll do, m is equal to d. So now we have that value inside I. Let me just check the loop. I will have to check the 7 week. Branching commands. We are almost at the end, but I can't find a loop example. There are none. Maybe we have it here. Yeah, it is over here. Yeah, we need to implement something like this. Okay, then instead of getting I, let's get N. Now N will contain this thing. I think this implementation will be easier and much more efficient. So let's just use I. Let's get the loop. But if we are going to use a loop, we'll have to use a counter. Yeah, we need a counter. So for that, EQE counter, func e count. Func dot loop. Func e count. Now we'll do something here. We'll get the I variable. Can do m is equal to m minus 1. And then we'll write the stop condition. So func dot stop func e count m we will jump if equal to 0. So suppose we have n was 2, that means we need two local variables. So I is already 2. In this case it will be 1. Well, let's not decrement it right now, so that we can write jump if equal to. So if equal to 0, we will jump and write it afterwards. But if it is not equal to 0, then we need to change the value at the top of the stack. So in this case we'll get the stack pointer. Oh well, we already have the code for the same, so let's copy this, paste it over here. We'll select the stack pointer and store 0 at that value at that position, and we'll increment the stack pointer. After that we will decrement I. After decrementing I, we'll do add func dot loop func e count. So, and after that we need to jump unconditionally at that point, so 0j. So this is what happen, this is what will happen when we come at this point. We'll store the address and we'll jump there unconditionally over here. Then we check for the condition. Wait, this is incorrect. Wait, this is not totally correct. We need to get I, so we'll do at I. Is equal to m. This will work. We need to write the stop condition as well. Stop label func dot top func e count. All right, we'll jump at this point, and when the loop is over, and guys, this is just for one line of code. Still need to write a hell lot of code for the right function. We have just written the code for push 0 n var times, and I'm not even sure if this works or not. What are we doing over here? First we are getting the function name and providing the label here. After that we are selecting argument 2, which contains the number of variables, and we store it inside data register. Now we store it inside I variable. After that we assign a label func.loop. Then we get the I variable again and store its value inside data register. Is this code uh, smaller than this one? I don't think so. They have used 3 variables in total. Well, if we compare it with our PS, they have used 2 variables and we have just used only 1 variable I. So I think our solution is better. Maybe not. Okay, so let's see. Where was I? First we get the value of I and store it inside data register. After that we get this label inside a wait. It should be capitals, and we check for the data register and check if it is equal to 0 or not. If it is equal to 0, we'll jump to this label, but if it is not, then we will assign the stack pointer, assign 0 on the top of the stack, increment the stack pointer. This we will do n-vars number of times. So when we enter this loop for the first time, I will suppose n-vars is 2, then in this case I will be 2. In that case we'll assign 0, increment the stack pointer, decrement I, and jump back to here. So now I is 1. Again we assign and decrement I. We jump back to this point. Now to decrement 1, decrement 0. Okay, so we'll have 2 zeros, but I think we have a bug. I do assign value. Yeah, this will work. So let's continue. After we stop the loop, what else do we need to do? This will be the state of the stack. After that, now we will wait, is that it? We assembly code that handles the initialization of the function application. This is the code for initialization. After that, yeah, this is it for this function. Oh, awesome. Don't need anything else. Because after this we'll continue with the rest of the code of that particular function. So this is it for the right function. That was not much, right? Let's copy this. If parser type equal to function return parser argument 1 arg1. Let's call it func command line. Now we need to copy all of this code from this point. Oops. What the heck? Right. Now I need to replace we still need to change some things. Like this. This should be changed as well. What else do we need to change? Okay, this is correct. We still need to get the func e count. We'll assign funky count over here. Yeah, everything else seems all right. Now we need to write parser.instruction, then func c, replace comma with new line character and write. Cool. After writing, we need to increment the funky count. Okay, wait, we have a bit of a problem. Func, so we need to write func self.func e count plus equal to 1, and here as well we need to change func e count. We need to change it to self dot func e count. the heck? Just this one and this one and this one as well. Okay, it's correct now. What else do we need to change? Func count. Well, now let's test the program. We need to call write function. Wait. There's an issue. We still haven't got the argument 2. Let's get it. Argument 2 equal to parser dot arg2. This will give us arg2. Okay, it seems correct now. Now let's call it from the main function, from the setup. And if p dot type equal to c function, did we write function or func? I guess it was function. Go dot call write function and pass the parser as well. This is for the function, and now we need to write the logic for, let's see, for the return statement. I will write it just after the function. Definition write return. Is it write return or something else? Yeah, it is write return and no arguments, just self. Let's figure out logic for this function. The statement will be something like this, just return. But there will be a lot of things we'll need to take care of. First, we need to get the end frame. We need to get the LCL pointer and store it inside a variable end frame. Okay. Are we storing the LCL pointer? Yeah, the value of LCL pointer. So if we write the pseudocode will be something like this. We'll have a variable. Well, let's just write the code directly. We don't need to write the pseudocode. So we'll first get the local pointer and we'll store its value inside the data register. After that, we will get end frame variable and store that value inside the end frame variable. First statement is executed. Now we need to get the return address. To get the return address, we will have to first do the steps end frame -5. Yeah, how are we going to get it? We shouldn't change the end frame variable because we'll need it again. Right, are we using the end frame again? Let's see. Yeah, we are using end frame over here, so we shouldn't really change its value. Okay, then we will need a variable named return address, and inside there we'll store this value, a return address value. I already have the end frame variable selected. What do I need to do now? Yeah, well, what if I do this? D is equal to m minus 5. No, I can't directly write 5 over here. I will need a temporary address variable. Before I do that, let's get 5 and store it inside the data register. Now we can do this. M is equal to D. Now this address contains 5. We can select the end frame at end frame. No. Yeah. D is equal to M. Now let's select the address register again. ADDR, and we will do M equal to D minus M. D contains the end frame and M has minus 5. So now we will have the address. Awesome. Now all we need to do after this step is D is equal to, no, we'll have to do A is equal to M. After that we can do D is equal to M. Now this D contains the value, the return address value. So now we can get the variable ret addr and assign m is equal to t. What if we had used this address? Yeah, it's all right. Can I just get rid of address variable and yeah, this is correct. We don't need to do anything else. We have implemented this instruction as well. Now let's do star arg is equal to pop. Pop, so we'll pop the value from the top of the stack. So we'll have to do this. We'll have to select the stack pointer. After that, what we will do, sp m equal to m minus 1, decrement the stack pointer. After that, we store the value inside the data register. We need to store this value at arg0. So let's get the arg arg is a pointer. Wait, this is incorrect. I have to do a is equal to m first. Now this will have the correct value. Same for this. I'll have to get a is equal to m first. Now I can do m equal to t. Okay, this seems correct. We have popped the value and stored it inside argument 0. Now what else we need to do? We will change the value of the stack pointer. It should point to arg +1. Okay. This A still contains, so when we do at arg, what this will do, A should be sure. A will be 400. Okay. This B equal to M plus 1, right? No, not M, A. Get the stack pointer. A equal to M. M equal to D. I think this is correct. But before that, do we even have this kind of operation? D is equal to A plus 1. Need to check. D is equal to A plus 1. Type C instruction. Destination D. Yeah. And computation A plus 1. Yeah, we have it. So this is legit. This is all right. What else can we do? We need to restore this, that, arg and LCL. We'll have to carry out the steps. to, let's see, yeah, up to this point. So let's copy it, paste, and before we continue, let me give some space between the different comment lines. So that I can know which command ends where. Okay, in this case I don't need 5, I will need 1, but because it is 1, I don't even need to store it inside data register. Wait, this seems, what is correct? Address is equal, m is equal to t minus m. We don't need this variables. I can first select the end frame, then store its value inside data register. Now I can select address register, variable solve, and I can do m is equal to t minus 1. Yeah, this seems correct. So it's value inside data register, and now instead of a return address I need to get that. M is equal to T, right? Now we'll do the same thing for this arg and local, but now we'll need this addr 5. Instead of 5 we'll store 2. All of the steps will remain same. We'll just need to change this return address to this. Okay, now let's copy it again. Instead of 2 we'll now have 3, and we'll store its value inside arg. Now we'll have 4, and its value will be stored inside LCL. Now after that we need to write this go to label. Go to return address. So we'll need this variable at return addr. Is that it? Can I directly jump now? 0 GMP. Is this correct, or should I do a is equal to n first? We'll see if this works or not. Let's just keep it this way for now. And I think we are done with the return address. And we have taken care of the return as well. Now all we need to do is write this logic. So let's copy this. Do we have any labels in this case? No, we don't have any labels, therefore we won't need the line counts. Good. This should be return arg1, and we don't have any arguments in this case, so it will be just plain what should we call this? Return C. Awesome. This is the longest function, I think. These are the written commands. Return C, replace dot comma with new line character. We don't need this variable. That is it. We should try to run this program and see if it works or not. We need to pass which function it is. Oh, before that, I think I need to change the main code to include this function calls. We have returned the condition for function. Now let's write the condition for return as well. Simple function call, simple function dot pm. Oops. Okay, right. Return. I think I missed something. Yeah, I misspelled this function name. What? Oh yeah, I see. Parser. Good. Yeah, getting the output. Let's check the output file. Yeah, we do have the output file. This is the output file. Okay, it seems correct. Let's try to run this program. We need the CPU emulator. CPU emulator. Let's open up CPU emulator. Function calls simple function dot tst. Let's turn off the animation. I'm sure it is not going to work first time. Yeah, that's what I said. We have an error. These are the values which we are getting, and this is what we should get. Wait, there's not much difference. This is the compare file. 300, 310, 410, 19, 11, 96. This is output 300, 310, 410. Yeah. RAM 0 and RAM 1. Oh, we are incorrect at only one position. This should be 312. Wait, this is the comparator. It should be 311. Instead, we are having 312. So that means our program is working correctly, but just one thing is incorrect. We are let's check where we are incrementing the stack pointer. We may be doing it over here. So first we get add to, we get the stack pointer. This seems correct. That means we might have a problem in return function, return instructions. We maybe let's check the file. Where are we incrementing the stack pointer? We are interacting with stack pointer over here. We are first decrementing it. Let me check the code. We are interacting with the stack pointer at this point only, which is I think this one. Yeah, no. Here we are popping the value of the pop of the top of the stack. So first we are decrementing the stack pointer, and assigning minus. Okay, this seems correct. The problem may be in this command. So yeah, what are we doing over here? We are getting d is equal to a plus 1. What is a? A is where arg is pointing. We are not changing the value of stack pointer anywhere else. I'm getting incorrect answer. Okay, we'll have to walk through the program step by step. That means let's do it. First, let's clear the RAM. We are going through a loop. So after this loop, we should have 2 zeros on the top of the stack. Let's see. Stack is right now pointing at 317. Right. Now 17, 18 and 19. Okay. After we continue with this push operations and pop, these are all correct, I think. What are we doing? We are pushing value, pushing two values, adding it. After that we are noting it, then we pushing another value, adding it, pushing another value, subtracting it. So after the steps, we had two local variables, and after that our stack pointer was pointing at 370, 18 and 19, right? And let's see what happens when we push, add, it stays at 319. No, it will be 320. When we not it, it will still be 320. 21, 320, 21, 320. Okay. I see. Wait, we are jumping at 19. What is that 19? Wait, this is incorrect. It's 19. 'Will execute return. Right now stack pointer is pointing at 320. what should we do here now? Stack pointer will pop the value of the top of the stack, store it inside argument, and stack pointer should be argument plus 1. Arg is 310. Yeah, right. And why is my script not working? To this point, everything seems correct, but what happens here is we try to jump to the return address. Okay. function should return get the return address. Do we even have the return address? Yeah, I don't think so. We have a return address. How about now? Nope, we still don't have the return address. Oh yeah, we have it now. This is the global stack. This is the return address 9. Oh, wait. Where's the code for function, not function return? There's no caller in this case. Is this the reason I'm not getting correct output? CPU emulator. I mean, at this point, I'm storing at 19 and I'm unconditionally jumping at that address at 19 means at this point. So this again changes the things, and Maybe what if I have to write the init code? That might be causing issue. Yeah, let's try to write the init code then. Where is it? So here at 256, and we have to write this init code. I think so. But there's no sys init in this function. In this file, we don't even have a sys init. And also we have not implemented the call instruction. You know what, I think this program is such that it doesn't have a caller, or we are not going to return to anything anyway. Where should we return anyway? Just tell me. Suppose if we were having a function, different function, we might have the return address of that function and we might be returning to that address, but that's no. Yeah, of course, we don't even have the caller function. So yeah, that's why it is not written. And anyway, everything else is working correctly. So I think our program is correct. If it is correct or not, we will figure it out later when we translate the program for this other files. If it is working for all of these files, that means it is correct. This seems an incomplete function because it is just testing for the function in return, but it can't test for return. We can't even return to any statement. Yeah, I think we'll see it later. This is it for today. It's been 6 hours. I don't want to do anything else right now, so let's just quit it. We'll come back to it again later. Alright, we'll try to debug this program later. I will see you guys again in the next stream.